So welcome back, students. So far we have discussed about how current flows in a conductor and what makes it flow in a conductor, and we also talked about resistivity and then the temperature coefficient of resistivity and the impact of temperature on the resistance and resistivity of a conductor, and the limitations of Ohm's law. And we also talked about cells, EMF and the internal resistance, and resistors in series and resistors in parallel, and all important Kirchhoff's laws, the voltage law and then the current law, and we also done some problems with the Kirchhoff's laws. We've done these things so far, and now we are going to use Kirchhoff's laws in some practical applications actually. Okay, the first thing that we would take up to do, that is the Wheatstone Bridge. So the Wheatstone Bridge is an instrument that allows us to calculate the resistance of an unknown resistor. Okay? You take something whose resistance you don't know, but then you're going to use the Wheatstone Bridge to calculate the resistance of that. And once you understand the Wheatstone Bridge, you will also be able to handle some of the circuit problems with much ease. Okay, we'll talk about all that now. So the first thing is the Wheatstone Bridge. We'll take it up now. A Wheatstone Bridge is something like this. So this will have 4 resistors connected like this. Okay, I'll call this as R1, and this is R2, this is R3, and this is R4. So this is A, this is B, and this is C, this is D, Wheatstone Bridge, and I will also have a galvanometer connected between B and D. So I'm going to have a galvanometer here. Okay, this is a galvanometer. The galvanometer will also have its own resistance. Okay, this is G right there. Okay, it will have its own resistance. So this is actually the Wheatstone Bridge. Okay, and I connect it to a battery. Okay. So now you see that I will be the current coming out to the battery, and then I1 will be the current flowing through this branch, and I2 would be the current flowing through this branch. And the current flowing through the galvanometer I will call as Ig, and then the current through this can be called as I3, and then the current through this can be called as I4. Okay, so and I3 plus I4 will again be equal to I, which should be. Okay, so I can write a few equations there. Let's see. If I take this junction A, then I is equal to I1 plus I2. Amount of current which is coming in must be equal to the amount of current that is going out. Then at junction B, okay, at B, what's the amount of current coming in? It's I1 and must be equal to Ig plus I3. Ig plus I3. Or I3 can be written as I1 minus Ig. Either is fine. Let us set B. And at D, what you have? At D you have I2 plus Ig must be equal to I4. So let's say I4 is equal to I2 plus Ig. Okay, so that is I4. And what about at C? At C, I3 plus I4. So I3 plus I4. That should be equal to I. How? Okay, what is I3? I3 is simply I1 minus Ig. I1 minus Ig. Plus, what is I4? I2 plus Ig. So you see that Ig and Ig will cancel. So I3 plus I4 is equal to I1 plus I2, and is equal to I. Okay. So the amount of current leaving the battery is equal to the amount of current entering the battery. So all fine. This is all done. Okay. Now we need to consider one case. So depending on the resistances, the values of I1, I2, I3, I4 and Ig will be different. But I'm going to consider one case where Ig will be equal to 0. So when would that happen? It would happen when potential at B is equal to the potential at D. If VB is equal to VD, then there is no potential difference, so Ig will be 0. Okay. So how and when can this happen? It's a question. What is the condition? What kind of resistances I must have here so that the voltage drop across this R1 because of I1. So I1 R1 must be equal to I2 R2. If I1 R1 is equal to I2 R2, then this potential and this potential will be same, then no current will flow through this. Then what is the arrangement of resistors I must have? Okay, so that this condition will be met. Okay. So when will Ig be 0? When VB is equal to VD. If VB is equal to VD, then Ig will be equal to 0. Okay. If Ig is equal to 0, what else will happen? If Ig is equal to 0, then what is likely to happen here? Well, then I1 will be equal to I3, right? If Ig is equal to 0, then I1 will be equal to I3 straight away. I1 will be equal to I3. And what else will happen? I2 will be equal to I4, because I4 equal to I2 plus Ig. If Ig is 0, then I4 must be equal to I2. And I4 must be equal to I2, or I2 must be equal to I4. So if Ig is equal to 0, when will that happen? When VB is equal to VD, this will happen. Okay. Suppose VB is equal to VD and there is no Ig. Okay. Let's see what will happen first. Okay. Let me use Kirchhoff's laws, or the voltage law, to see what will happen when Ig is equal to 0. So let me take this loop. Okay. This loop A, B, D, A. Loop A, B, D, A. We take this loop. Okay. Now that I know the current directions, I have the current directions. I can't say I know the current direction. Now I have the current directions. Assume current directions. I'm going to assign potential drop signs here. I1 enters here, so this is plus, this is minus. Ig enters here, so this is plus, this is minus. I2 enters here, so this is plus, this is minus. I4 enters here, this is plus, this is minus. I3 enters here, so this is plus, this is minus. All done. Okay. Now I can do the looping now. I can start from A, I can come back to A, either clockwise or anti-clockwise. I will do clockwise. I won't do it this way. I'll start from A. What's the first one? I1 R1. That's the voltage drop. That is plus, because I'm entering plus, right? So I1 R1. And then I come here. Ig is a current flowing through it. Then Rg is a galvanometer resistance. Okay, Rg is a resistance. Ig, Rg. I'm entering again plus. So plus Ig, Rg. Then I come back here. Then I'm entering through the negative terminal. So minus. So I2, R2. I2, R2. Now we come back to the same position A. So the sum of the voltages must be 0. Okay, this is the first equation. Right? Okay. Then this is the general equation. This is for any Ig. But now what have we considered? I have considered a case where Ig is 0. If Ig is 0, then this will be gone, right? This will be gone, then I will have I1 R1 is equal to I2 R2. So, which means I1 by I2 is equal to R2 by R1. Okay? So, you got it. Then what else now? Then I will take this loop, the second loop. Again I will do a clockwise rotation. Start from B, come back to B. So now what is the loop? Loop BCDB. BCDB. So I3 R3 plus, right? I am entering plus. So I3 R3 plus. And then it's I4 R4 minus, because notice here I am entering in through the negative terminal. So I am going to have minus I4 R4. And then here again I am entering through the negative terminal, right? So minus IG RG. And come back to B. So it's equal to 0. So this is for all currents. Okay, this is for all value of IG. But what have we considered now? I have considered a case where IG is 0. So what will happen here? This will become 0. If that becomes 0, what will happen to I4? I4 will become I2. Right? What does it mean? So if there is no current contribution here, then I2 current that is coming here will flow through I4 only. There is no addition or subtraction of that current. So this will give me I3 R3 minus I2 R4 equal to 0. So that will give me I3 R3 is equal to I2 R4. So what is I3 again? What will happen to I3? If Ig is equal to 0, then I3 will also be equal to I1, right? So now that will also become I1. Okay? That will also become I1. I1 comes here, Ig is 0, so I1 must go through this. So I3 will be equal to I1 when Ig is equal to 0. So I1 R3 is equal to I2 R4. So what is I1 for I1 by I2? You will have R4 by R3. So this is equation 1 and this is equation 2 for me. Okay? So now, what do we know? I know 1 is equal to 2. So I1 I2 is equal to R2 by R1. I1 I2 is also equal to R4 by R3. So which means R2 by R1 is equal to R4 by R3. Or the reciprocal of it. R1 by R2 will be equal to R3 by R4. Both will be the same. Well, this is called as the balancing condition. When you have this condition, we say that the Wheatstone bridge is balanced. The bridge is now balanced. Okay? So what does it mean? In the balancing condition, when the balancing condition is met and when the bridge is balanced, no current will flow through IG, even though you have a link there. It's like it's open. Okay? It's not. This won't even take part in the circuit when this condition is met. So it's called as the balancing condition. So let me try to give some numbers. For example, let's say R1 is 10 ohms. Let's say R2 is say 5 ohms. Okay? Now what do you have here? 5 by 10. R2 by R1 is 5 by 10. Or R1 by R2 is 10 by 5. Doesn't matter. Either is fine. Then that must be equal. R2 by R1 must be equal to R4 by R3. See, here to there, here to there. Okay. And then let us say that this is, let's say this is going to be 100. R4 is 100 ohms. And this should be 200 ohms. R3 must be 200 ohms. So you have 10 and 200 there, 5 and 100 here. Then 10 by 5 is equal to 200 by 100. In either case it is 2 is equal to 2. Or 5 by 10 is equal to 100 by 200. In both cases it is half is equal to half. Okay. When you have this kind of a condition, then Ig will be equal to 0. You can straight away say it. By looking at the resistances, you can say whether it is balanced or not. If this condition is met, it's balanced. Then Ig will be equal to 0. It's as simple as that. Okay? So, this is the principle behind the Wheatstone Bridge. Okay. So, if you have different resistances in this bridge, again all the currents will be available. Even Ig will not be equal to 0. But in this balancing condition, when this is met, R1 by R2 is equal to R3 by R4. When that condition is met, then Ig will be equal to 0. No current will flow through Ig. So you can just take it away. It's as good as not connecting any galvanometer there. It's as if it were not present in the circuit. Okay. That is what we call as a balancing condition. Well, how can I use this to find an unknown resistance? Let us suppose I have an unknown resistance. I have a resistor whose resistance I don't know. Then what I'm going to do is I'll take 3 variable resistors. Okay. Let's say R1 could be a variable resistor, and R2 could be a variable resistor, and R4 could also be a variable resistor. Then I can connect this unknown resistance here as R3. Okay? Should I connect it only at this position? No, that's not needed. I can connect it anywhere else too. Doesn't matter, first of all. Wherever I connect, this will work. But I'm choosing this as the place for unknown resistance. So I connect the unknown resistance here. Okay? Now what will I do? I don't know this value. But I'm going to change all the other resistors, R1, R2 and R4 in such a way that there is no current that flows through this. So that is Ig must be 0. I'm going to adjust this in such a way that Ig must be equal to 0. If no current flows through this galvanometer, what do I know? I know that R1 by R2, whatever value I have because of the adjustment, that R1 by R2 will be equal to R3 by R4. So I know the value of R1 because I've adjusted it. It's a variable resistance. And I know the value of R2. Then I know the value of R4. Now I can know the value of R3 because this condition would be met when no current flows through it. So that way I can know the unknown resistance value in the circuit. Hope this is clear to you. Okay, let me try to use the principle of the Wheatstone Bridge to find out the effective resistance of a complex circuit. The circuit will look fairly complex, but you can find the effective resistance very easily by using the principle of the Wheatstone Bridge. For example, I'll take this circuit. I have this kind of an arrangement. I have this kind of an arrangement. Okay, so this is point A, this is point B, let's say this is point C, and this is point O or D. So now they will want you to find the effective resistance between A and B. Okay. Let us suppose all these resistances are equal. Maybe this is 2 ohms, and then this is also 2 ohms, and this is 2 ohms, and this is 2 ohms, and this is 2 ohms, okay. And this is 2 ohms. Okay. Now you need to find the effective resistance of this. Then how do we do this? That's the question. Okay. Okay. So this is the this is the place where you need to find it, right? Note here, this is fine, but you see, you can't just take 2 and 2 here but then they are connected to the other 2 things now. And that this 2 is common for this 2 also. Finding the effective resistance is going to be a little tricky and difficult in this case. But there is an easier way of doing it. It will work only in these special cases, not in all cases, but it will work in certain special cases. Okay, let's see this. Look at this. 1, 2, 3, 4, and then a central resistance. Does it look like a Wheatstone bridge? Yes, right? It's like this. 2, then 2, then 2, then 2, then 2, right? 2, 2, 2, 2, 2. So that is how it is, this top portion. So this is A, this is C, this is B, and then this is D. Okay? Let's see if you have a Wheatstone bridge kind of a thing here, let us see if this is balanced. If it is balanced, then you know that there is no current that will flow through this, which means it's open. It's like this doesn't even participate in the network. Let's see if it works. R1 by R2, 2 by 2, that is 1. Is it equal to R3 by R4, 2 by 2? Yes, it is. Okay, so this is balanced now. Between these two potentials, A and B, 2 by 2 is equal to 2 by 2, which means that this is not considered. No current will flow through this. Okay, now I can ignore this. Okay, I can ignore this one. So this circuit gets reduced to 2, 2, this is C, this is A, this is B, and then 2, and then D, 2, right, this one, and then 2. Okay, so I have to find effective resistance between these 2 points. Is it easy? I have 4 there, right? 2 plus 2 is 4, and then I have 4 here. Then 4 in parallel will give me 2 ohms. 4 into 4, 16, divided by 4 plus 4, 8. Then that will give me just 2. So this will be 2, 2 in parallel with 2, and that will give me 1 ohm. So the effective resistance of the entire network is simply 1 ohm. How? Note here. So it's like this, right? This is 4, then this is 4 again, and this is 2. The effective resistance will be 1. Because this condition is met. But they all have different resistances. The balancing condition may not be met. In that case, you can do it very easily. It will be difficult. But in this case, it will work. It's because you are finding the Wheatstone bridge balancing condition. Okay, it will work even if this is say 10 ohms and this is again 10 ohms. Then also you see R1 by R2 is equal to R3 by R4. Then also it will be gone. But then you will have 4 and then you will have 20 here and then 2 here. Or this can be 20 and this can be 20 also. Then also it will work. Because 20 by 10 equal, right? So then I can ignore this. Then it is simply 20 plus 20, 40, 10 plus 10, 20. Ignoring this completely. They are in parallel. So 40 and 20 will give you 800 by how much? 800 by 60. So 8 by 6. That would be the resistance of these two, and that in parallel with this two. So then I will get a different resistance there. So that is how it is going to work. Okay. So this will work that way. So Wheatstone bridge, the idea, the principle of a Wheatstone bridge can be used to find resistances like this. The effective resistance of circuits like this very easily. Hope this is clear to you. Okay, now I will take example 3.8 and try to do that problem. So the problem is this. The four arms of a Wheatstone bridge have the following resistances. AB 100 ohms, BC 10 ohms, CD 5 ohms, and then DA is 60 ohms. Now a galvanometer of 15 ohms resistance is connected across BD. Calculate the current through the galvanometer when a potential difference of 10 volt is maintained across AC. Okay, so let's see what happens. So I have this circuit. Galvanometer, and then this one, this one, and then I'm connecting a battery here. It's a Wheatstone bridge. This example 3.8. Okay, so the voltage is 10 here, 10 volt. And then I is the current out of the battery, and I will be the current into the battery, same current. Okay. Now this is 100 ohms, and this is 60 ohms, and this is 10 ohms, and this is 5 ohms. Okay. You can say that this is not a balanced bridge. Why? Because 100 by 60 is not the same as 10 by 5. 10 by 5 is 100 by 60. This is 10 by 6, that is 10 by 5, not equal. So the bridge is not balanced, which means the current through the galvanometer is not zero. There will be some current flowing through the galvanometer. So it's a different problem. It's not the same problem that we did before. Okay. So this is 15 ohms. Galvanometer resistance. Okay. This is I1. And then this is I2, and what happens here? So this is IG, current through the galvanometer. So what will this be? If we take this one, this is going to be I1 minus IG, right? I1 minus IG. Right? Okay, this is going to be, let's say if we say it's I3 plus IG will be equal to I1. So I3 will be I1 minus IG. Straight away you can do it. Likewise, what do you have here? So IG is coming here, I2 is coming here, so this must be I2 plus IG, which is equal to I4. Anyway. So that's about it. I mean, you can add it, right? I2 plus IG, I1 minus IG. So when you add these two, IG and IG will cancel. Then you will have I1 plus I2, which is anyway equal to I. So all tallies properly. Okay. Now I need to find this current. Okay. So how many unknowns do I have after this? I have I1, and then I2, and then IG. These are the three unknowns I have. Because this is not an unknown, right? Now if you know I1 and IG, I can calculate this. And if you know I1 and I2, I can calculate I. If you know I2 and IG, I can calculate this. So no problem. So the only three are unknowns. I1, I2, and IG are my unknowns. So I require three equations to solve. Okay. So how am I going to solve them? Well, I can take three loops. First let me take this loop. But before that, this is the current. This is the current, right? Current direction I assume. So since I have assumed the current direction, I am going to have this as plus, this as minus, this is plus, this is minus. It comes here. So this is plus, this is minus, goes there. So this is plus, this is minus, goes there. So this is plus and this is minus. Now I have given the plus and minus signs for all the resistances. Now I am ready to do my loop law. Okay. So I am going to start from here. Let's say this is A. Let's see. I think I've lost it. Okay, let's see. what I'll do, I'll label them properly because I've lost the labels. So I'll go with the labels in the textbook. So this is A, B, C, D. A, this is B, this is C, and this is D. Okay, so this is a voltage channel. Let's see. Let me take this loop A, B, D, A. So loop A, B, D, A. So what will happen here? I1 into 100. So 100 I1, that's positive because I'm entering it in the positive, to the positive terminal. I come here. I enter this also to the positive terminal, right? So Ig into 15, so it's going to be 15 Ig positive. Then I come here, then it is 60 into I2 but negative. Minus 60 I2, that is equal to 0. And down. Okay, that's the first equation. Okay, then what's the second equation? Okay, I'll take this one. This loop as second loop. So now that is loop BC DB. BC DB. I'll start from B, come back to B. I'm entering to the positive here, right? So that is 10 into I1 minus Ig. So 10 into I1 minus Ig. That's the current. Then here I am entering in the opposite direction. So that is minus. That is 5 into I2 plus Ig. 5 into I2 plus Ig. And then I come here. Again I enter through the negative terminal. So that's minus. So now 15 into Ig. That must be equal to 0. Can I reduce it now? So this is 10 I1 minus 10 Ig minus 5 I2 minus 5 Ig minus 15 Ig equals 0. So it's simply 10 I1 and then minus 5, or rather I should say minus 10 minus 5 minus 15, 15 minus 30 Ig minus 5 I2 is equal to 0. So if I divide the whole thing by 5, then I'm going to get 2 I1 minus 6 Ig minus I2 equals 0. You do the same thing here, right? And that will give me 20 I1 plus 3 Ig minus, how much would that be? 12 I2 be equal to 0. I will reduce this. Reduce this. I got two equations. And the third equation, well, I can take this, right? I can take this loop. So that way I complete all the branches. No branches left now. So loop A, D, C, A. A, D, C, A. It's like that. Okay. So I'll start from here. Then I2 into 60. So 60 I2. That is positive anyway. I mentioned to the positive one. And then 5 into I2 plus Ig plus 5 into I2 plus Ig. And I enter minus, right? Minus 10 volts. Negative terminal. So I'll come back to A. That is equal to 0. So can I do this now? 60 I2 plus 5 I2 plus 5 Ig is equal to 10. Okay, that is 65 I2 plus 5 Ig equals 10. And that will be 13 I2 plus Ig equal to 2. Okay, reduced to Ig equation. So this is equation 1, this is equation 2, and this is equation 3. Okay. So I must be able to solve these three equations to know the values of I1, I2 and Ig. Okay. How do I do that now? Well, from this equation I can write I2 in terms of Ig. Let's see what happens now. So what is I2? I2 is going to be equal to 2 minus Ig by 13. That is it. So can I go also put it in here? If you put it in there, what do I get now? So I get 2 I1 minus 6 Ig, then minus I2, 2 minus Ig by 13 equals 0. So take 13 common. So 13 into 26 I1 minus 6 into 13, 78, right? 60 plus 3, 78 Ig. 78 Ig. So I got I2, so this will become, okay, this will become, okay, minus 2, then this will become plus Ig divided by 13, divided by 13 is equal to 0. So I will take 13 to the other side. So it is simply, so 26 I1 minus 78 Ig minus 2 plus Ig is equal to 0. So that gives you 26 I1 minus 77 Ig, right? 78 minus 78 plus Ig. So 77 Ig is equal to 2. Okay. So now I can express I1 in terms of Ig. You can do that. That's it. So I1, what is it? So I1 is equal to 2 plus 77 Ig by 26. Okay. Now I expressed all of them, both I2 and I1, in terms of Ig. Okay. So I should be able to solve for Ig using the third equation. I'll go here. So 20 into 2 plus 77 Ig by 26. That's I1 plus 3 Ig. Okay, then minus 12 into I2, which is 2 minus Ig by 13. That must be equal to 0. So you see, now you got only Ig here, then all the others are just numbers. Okay, I'll take 13 as the common thing. So that will give me 10 by 13, right? So 10 by 13. So I have 13 here, I have 13, so it's very easy if I will do it now. So that gives me 20 plus 770 Ig by 13 for that, and plus 3 into 13. I take LCM. 3 into 13 would be 30 plus 3, 39. So 39 Ig by 13 plus or minus, you get 12 into 2, minus 24, then plus 12 Ig by 13 equals 0. So I can remove 13, all the 13 here, they will go to the other side, 0. So that this is the final thing, right? So what do you get here? So you got 12 Ig, 39 Ig, 77 or 770 Ig. So 770 plus 39 plus 12 is, this is going to be 41, 51, then 770 would be 821, right? 821 Ig, 821 Ig, okay, 821 Ig. This is equal to minus 4, right? 20 plus minus 24 is minus 4. So if it goes the other side, 821 Ig is equal to 4. So Ig is equal to 4 by 821 amperes. Okay. So that is 1 by roughly 200. So it's so 0.005 less than that. That is the value of this. So actually what you get out of this is Ig is equal to 4.87 milliamperes. So Ig is equal to 4.87 milliamperes. Let's see if this is correct by that's the answer given in your book. Let's see if that is what we get. So 4 divided by 821, yes, we get 0.00487, so that is equal to 4.87 milliamperes. That's the amount of current which will be flowing through Ig. Note that Ig is not 0. Why Ig is not 0? Because the bridge is not balanced. Why do we say that? Because you see the ratio is not the same. It's 10 by 6 on this side and then 10 by 5 on that side. So it's not balanced. So Ig, you will still have some amount of current flowing through it. Instead of 60 ohms, if I add 50 ohms, then Ig will be 0. Why? Because 100 by 50, which is equal to 2, the same as 10 by 5, which is equal to 2. So instead of 60 ohms, if I add 50 ohms, then Ig would have been 0. But now I have 60 ohms, the bridge is not balanced, some current will flow through Ig. So this is how you do this type of problems. Hope this is clear to you.